Let's move on to the next talk. Professor Balasubramanian is going to talk about analytical number theory in India.
Thank you. Thank you very much for this invitation. Let's talk about analytic number theory in India. This is, in some sense, a continuation of an earlier article which I wrote that came in the proceedings of the ICM 2010, and where I discussed the development of number theory in India, especially covering the period from Srinivasa Ramanujan, because a lot has been written about Srinivasa Ramanujan, but then about the number theorists who came a little later, like Anandarao or Pillai or Vijay Raghavan, nothing much has been written, and I thought one should probably have those things written. And that essentially covered time till independence. And this is what I plan to continue, and we shall continue this thread and discuss the development of analytic number theory from 1950 to 2000. And for those who are interested in a little later, like 2000 to 2010, there's a beautiful article by Ritabta Munshi, which appeared in the Indian Journal of Pure and Applied Mathematics, where he covers the period between 2000 and 2010. And he gives two reasons for covering up to 2010. And the first reason is in 2010 is when we had an ICM, and one could have probably see what is the number theory before 2010 and what is after 2010 to see whether conducting an ICM had any effect at all in the development of the number theory here. And there is a second reason to which I will come a little later. Yeah, as I told, I was essentially talking about the number theories of that era, which includes people like Chawla and Pillai. And in that article I wrote, with the departure of Chawla to the United States in 1948 and the death of Pillai in 1950 in an air crash, we leave the first epoch of the development of analytical number theory in India and enter the second. I mean, this first thing and then we second. And again I wrote, if a single event can be said to mark the beginning of this epoch, it's not only in number theory but in any area of mathematics, it is the emergence of the School of Mathematics at the Tata Institute of Fundamental Research under the guidance of K. Chandrasekharan. I mean, to have an institute exclusively devoted for mathematics and having everybody there has always its great effect rather than single individuals working at various places. And of course, most of you would have heard about Chandrasekharan, more as an institute builder rather than a mathematician. He was a great mathematician, but he was much greater institute builder. And in fact, he was not actually the first HOD of TIFR. The first HOD was D.D. Kosambi, and D.D. Kosambi was interested in mathematics, statistics, philology, history and genetics. And therefore, as a great scientist, he was very great. But on the other hand, Chandrasekharan was not only a great scientist, but a great institute builder. Therefore, let me say something about what he did. KC, as an institute builder, KC joined TIFR in 1948. He was a great institute builder. He persuaded the leading mathematicians like Ambrose, C.L. Siegel, about which I will take a little later, Eilenberg, Rademacher, Maas, Eichler, Zariski, Schwartz and others to come to TIFR, teach graduate courses to the students so that the students had an opportunity to learn good mathematics from the great mathematicians, and then the lecture notes were written, and that is essentially the. And he also had a 4-year colloquium on various subjects. And regarding this, let me first quote Seshadri about this is what appears in the obituary of which is Seshadri wrote. I still remember that when I met John Coates for the first time at a metro station in Paris, the first question he asked me was, how did you manage it? Meaning, how we were able to build a first-rate mathematics center in India when at that time there was no comparative institution for mathematics in Australia. Therefore, I mean that achievement of building a great mathematical institute was essentially due to Casey. And in Emerson says, MS Narasimhan, in the span of 15 years, Casey set up an institute in India which was soon recognized internationally as a leading center of research. And Schwartz writes, this is important, I consider the School of Mathematics of TIFR is a remarkable achievement and is without a parallel in any other country. And that's what exactly Casey did. But on the other hand, Casey was also a great, because now I am going to talk more about the Casey as a number theorist. And in my earlier article, again I wrote, Chandrasekharan's work with Raghavan Narasimhan were the first major work done in the theory of zeta function in India after Chawla. And therefore, probably I should say something about Raghavan Narasimhan also. Raghavan Narasimhan did some number theory in his middle period, which is again what we are going to concentrate, but started more as a person working in functions of several complex variables in the beginning, and he ended also as a function working with the function of several complex variables. That was his forte. And he solved a famous problem in a complex variable called Levy problem when he was 23, on the basis of which he was invited to the ICM. And anyway, we are not going to talk about his work on the complex analysis, which is a major work, but let me just talk about what they did. Yeah, this is Chandrasekharan and Raghavan Narasimhan. Okay, therefore, anyway, when I say analytical number theory, etc., it means a study of the Riemann zeta function and then arithmetic function using the Riemann zeta function. And therefore, I think it's better to fix up some notations of what we are talking about. For a sequence of complex numbers an and a complex number s, one considers the generating Dirichlet series summation n power minus s. And for those of you who might not have seen this, and the fact is, generally we are accustomed to writing a complex number generally as z and its real part as x and imaginary part as y. But on the other hand, this theory was developed at that time when the notations for complex numbers were not well settled. At that time, Riemann used the notation S for a complex number and sigma for its real part and T for its imaginary part. And therefore, as far as the number theorists are concerned, when you say a complex number, it will be always S is equal to sigma plus IT, unlike Z equal to X plus IY for others. This series is convergent in half plane, and in most of the applications we are going to discuss, we will admit a meromorphic continuation throughout the complex plane, and that is very important that it has a meromorphic continuation. And in fact, this zeta function, in particular if n equal to 1, then the resulting series is called the Riemann zeta function. And as I told you, this meromorphic continuation is very important because this particular function was originally conceived by Euler. And still it is called the Riemann zeta function essentially because Euler did it only for real variables and Riemann was the one who did it for the complex variable and for analytic continuation. Riemann proved that this function has an analytic continuation with a simple pole at s equal to 1 and also satisfies a functional equation. These are the things which we will be needing when we talk. More precisely, I should write what the functional equation is. It is psi s equal to s into s minus 1 by 2 pi power minus s by 2 gamma s by 2 zeta s, then psi s equal to psi 1 minus s. Among the contribution of Hardy, one should mention the first approximation theorem, because this is again something that we will talk about. That is, zeta of sigma plus it is around 1 over n power s n less than or equal to t, where capital T is less than or equal to t. Oh, you should have written. This works when sigma is positive. Yeah, this works when sigma is positive. That's okay. That's what I should have mentioned. Forgot. You see, the point is, you are taking the zeta function and it is not given by the series summation 1 over n power s at that place, because you are now looking at a place S where the function is not convergent. Okay, convergent only when the real part is bigger than 1, but you are taking a place where the real part is less than 1 but positive. Therefore, to say that a function which is not even convergent, but the partial sums appropriately chosen actually approximates the function, is something which is slightly interesting and turns out to be very important. And the approximate functional equation, which is again the same thing. I mean, that you take the zeta function and take the partial sums, you take the chi s into zeta s, zeta 1 minus s, take the partial sums, add it, and it approximates the zeta function even at a place where this series are not convergent. Okay, it is easy to see that the functional equation, that the zeta function has zeros at negative even integers, therefore at minus 2, minus 4, etc. And the celebrated Riemann hypothesis states that all the non-trivial zeros have their real part equal to half. Anyway, okay, what is our interesting question? The question is, we would be interested in deducing the asymptotic formula for the symmetry function of an from the analytic properties. Therefore, you study sigma an into n power minus s and then try to deduce something on the asymptotic formula. More precisely, we would like to prove that summation an is some capital M of n and plus E of n, where capital M is the expected main term, the dominant term, and En is an error term or the secondary term. Results of the type En is small as a function of n, to say that Mn is around n and En is around less than square root of n, those results are called O results. And En cannot be very small. There are n's for which En is at least as big as n power 1/4 or something like that, will be called omega result. Okay, now we go to the work of Chandrasekhar and Narasimhan. Chandrasekhar and Narasimhan considered the Rees mean of the sequence, which is, and then used it to get the O result and omega result for the symmetry function. And I need not say how important the result is, just to say that it got published in Annals 1962. And they applied this to study special arithmetic function like a divisor function, Euler-Phi function, etc. In 1964, for the same thing, they obtained the L2 estimates for the error term. In 1963, they proved, this had turned out to be one of the very important papers quoted again and again, that for any Dirichlet series that has a functional equation, under some mild condition, one can write an approximate functional equation. Remember, this was done by Hardy for the zeta function. But then they said that you don't need to just restrict yourself to zeta function, take anything which is a functional equation. From such a generated setup, they could get an approximate functional equation for the zeta function of number fields, because the zeta function of number fields, etc., do have a functional equation, and then they were able to do a lot on that. This idea has been extensively used by the later authors. Now we leave it at that, and then Raghav Narasimhan left TIFR around 1964, and Chandrasekharan left it around 1965, and therefore now there was somebody was needed to really have the number theory developed in Tata Institute, and that was aptly filled by Ramachandra. And in the rest of the talk, probably next 10 minutes, I will be just talking about some work of Ramachandra. And in fact, I already mentioned about Munshi's article covering the period 2000 to 2010, and one reason he was closing in 2010 was essentially because of the ICM, and the second reason he writes, At a more personal level, K. Ramachandra, who spearheaded research in analytic number theory in India, passed away in January 2011, bringing an end an era. Therefore, if at all you want to say that the second epoch, which is around from the independence to 1990, etc., it was essentially dominated by Ramachandra in analytic number theory. Ramachandra joined TIFR as a student in 1958. See, most of us would join a research institute immediately after our MSc, but due to some personal reasons, Ramachandra could not join immediately, and therefore he joined a couple of years after he finished his MSc. And but already he was well equipped to start a research career. And looking at that, KC decided that Ramachandra need not undergo the standard customary graduate courses. And probably Ramachandra was the only exception who did not have a graduate course. I don't know what would have happened if he had gone to the graduate course. Yeah, he was inspired by, at that time, again as I was telling, KC was getting great visitors to Tata Institute to teach to the young kids. And that year it was C.L. Segal. And Ramachandra was inspired by the course of lectures given by Segal and wrote his thesis on a problem suggested by Segal under the supervision of K.G. Ramanathan. And I am not going to talk much about things. This is Ramachandra and this is K.G. Ramanathan. Okay, I'll just say what this thing is. Mathematical reviews. Eichler starts with the comments on this paper. This paper contains some remarkable new results on the construction of ray class fields on an imaginary quadratic fields. Okay, and I don't think I will be able to explain any of those terms now, and that would already cross the time limit which Ravindran has set. And in this paper, he also constructed a set of units and evaluation of certain elliptic integrals. And he got interested in these elliptic integrals essentially because they were constructed by Ramanujan. Then I should probably say something more. Ramachandra is not really a very good communicator, either orally or write. It is a little difficult to understand. And I can count myself as one set of people who could understand him. And I had to, because I have taken I have decided to join him as a student, and I cannot now give an excuse that I cannot understand what you are saying, and therefore, I had to force myself to understand what he has to say, and turned out to be more or less I am the only person who could really do that. And in writing also, he was not very good communicator. This is important because in 1970 ICM, H.M. Stark was giving a lecture, and where again he was essentially talking about the construction of the ray class field, which at that time was a conjecture, which was a very important conjecture. And then before he finished that thing, before he gave the lecture, Ramachandra came up with his beautiful proof, and therefore he has to add a few lines that this conjecture is now no more a conjecture, it is a proof. And that's exactly what he writes. Unless I have missed something, the proof is a simple matter of deciphering the notation of Ramachandra and applying his results. Okay? That's what it is. And then he did something on transcendental numbers. Since I don't have time, I have to. Okay. The youngsters can see on Ramachandra's contribution to transcendental number theory. And it's around the time Baker proved his important theorem, and Ramachandra, along with his student T.N. Shori, made some important contribution towards the theory and applied it to a whole of differential equations. That itself is a great thing, but I am not going to talk about that because for two reasons. Number one, it's a lecture on analytical number theory, and number two, I was nowhere involved in those work, and therefore I cannot talk about myself if I start talking about that. Okay, around 1970s, his interest towards theory of Riemann zeta function. It is at that time I joined him as a student, and we shall briefly discuss some of the results which came out of Ramachandra school. Let Fs equal to sigma an by n power s be a Dirichlet series which is absolutely convergent and admits an analytic continuation. Let T and H be two parameters. Here H is a small power of T, and Ramachandra found a method of getting a lower bound for the L1 norm and the L2 norm of f of it in this interval. And this turned out to be rather very important. In particular, he proved the results of these types. Okay, this is appeared in my thesis. My thesis also contains some results related to the result of Titmarsh on the L2 norm, and a method called multiple averaging to get the O result. And Hardy was the first one who proved that there are infinite limit zeros on the Riemann zeta function on the critical line. And he proved that if h is equal to t power 1/4, then you can find out a t in the interval t to t plus h such that the zeta function vanishes at O plus it. Though the multiple averaging and the lower bound for the L1 norm due to Ramachandra enables one to conclude the same for h equal to t power 1/6, improving the result of Hardy. Ramachandra showed how to get the lower bound for the fractional powers of zeta function, and about which Heath wrote that he could not even believe that the results would be correct at all. And these results turned out to be very important for trying to see the random matrix theory, how much it can apply to the Riemann zeta function. Therefore, these are the type of results which he proved, and this appeared in that. And Ramachandra used this method to get an omega result for the values of zeta of O plus it. For example, it is known that zeta of O plus it can be bounded by exponential constant times log t by log t. And now it is possible the omega result, which means that it is at least as big as exponential constant times log t. And Soundararajan, I don't know how many of you know him, I mean probably. Okay, Soundararajan observed that this method gives a value of 0.57, which remained the best for a long time until Soundararajan showed how one can take c equal to 3.7 using this resonance method. And I was talking about the lower bound for the things, and if you are thinking of an upper bound for the moments of the zeta function, the best results for the upper bounds are due to Soundararajan. Another important application of the lower bound in short intervals to get omega results. Okay, these are the things. And let me not briefly discuss the content, but just say why it is important. Yeah. Ramachandra observation, you see, first of all, if you have integral t to 2t f of a plus it whole square dt is bigger than t constant times t square, then you will get an omega result. E of t is O of t power a. And the only thing which you need is a certain sort of a holomorphicity. And Ramachandra's observation was that the result remains valid even if there are a few singularities, which it turned out to be important because in most of the problems there will be singularities, and therefore you cannot apply the standard Perron's formula and there are standard Parseval's formula, and somehow you have to handle it, and Ramachandra was the first one who showed somehow how to handle that. Yeah, for example, he applied it to the function zeta 2s, zeta 3s by zeta 6x. Okay, this method turned out to be powerful by many to prove omega result. Therefore, let me just quote from Kortner and Novak. The method of proof, which turns out to be appropriate in this problem, goes back to the ideas due to Ramachandra, Balasubramanian, Ramachandra and Subbarao. They have been worked out in papers by Schinzel, Kulitner and the authors. I mean, many papers came actually explaining the ideas behind that. And this is the one thing which I want to talk and then prove. The method of proving non-vanishing on the line is to connect the value of zeta of 1 plus it and 1 plus 2 it. This method also gives a zero free region. And Ingham observed that without connecting 1 plus it and 1 plus 2 it, you can argue only at 1 plus it using the following identity due to Srinivasa Ramanujan. This gave a non-vanishing but not a zero free region. And Ramachandra observed that one can also get a zero free region from this identity of Ramanujan. Now, in the very funnily, 1930, Ingham proved it, and I think there has been no development at all on that observation. till we came around 1976 to make a thing, and again around for 30 years there has been no improvement at all. But now recently people have started thinking that this idea can really be used. For example, Peter Sornack has used this idea, and Humphreys and Brumley, let me quote it, the method of proof is of particular interest. It is essentially a generalization from GL1 of AQ to GLN of AF of the method of Balasubramanian and Ramachandra. How much Ramachandra would understand that and appreciate that is one thing that we see. Ramachandra developed a method to deal with overresult for the summatory functions, and in order to show the error term solved, we will ordinarily move the line of integration. In a number of interesting cases, this is obstructed with the presence of algebraic singularities, and Ramachandra developed a method called Cooley-Huxley contour, essentially using the fact that the number of singularities are small to really do the things, and this is one of the very nice paper of Ramachandra in Acta Arithmetica. This still remains the best method for getting summatory function. Okay, I think I would stop there.
Us.
Thank you.